Everyone, my name's Pete Regas, and I'm a member of the McMahon Lab at Cornell University. And for this session that's focused on simulation methods and implementation, I'll be discussing variational quantum algorithms for PDE measurement extraction. First, to begin with a presentation overview, I'll be discussing a variational quantum algorithm due to Bosch et al. In addition to having to be able to apply this algorithm, we're going to have to look at the ZGR QFT ansatz, and from which we'll provide applications of the quantum algorithm for solving other partial differential equations. And finally, we'll be discussing the results that we're able to generate with Circ for our noiseless quantum simulations. First, we'll begin by reviewing the Bosch et al. Variational quantum algorithm that was recently introduced in their paper titled Variational Quantum Algorithms for Nonlinear Problems. In the first step, to solve partial differential equations, including the Invissid-Burgers and Schrodinger equations, they formulate a cost function, which in the case for the Invissid-Burgers equation is given by the expansion of this norm, which involves a difference between a time-evolved variational state for a quantum solution, in addition to a variational state that's given in a previous time step that's acted on by a quantum operator. And our goal is to variationally modify parameters on our quantum circuit so that we can obtain readout for solutions. And after having obtained the cost function from rearrangements of the square of the norm, they can obtain a resultant superposition that they would like to optimize to find the ground state. And in addition to the cost function that's formed in steps 1 and 2, there are two backpropagation loops with the quantum nonlinear processing unit, which is a main feature of the quantum circuit architecture, in which states are acted upon by unitary transformations beginning from the 0 state that are given into input ports in the quantum nonlinear processing unit. And in the first backpropagation loop, there's an interface between the cost function and CMPU, in that the cost function informs the quantum readout in the measurements that we can abstract from the quantum circuit, in addition to a backpropagation loop 2 that involves going from the CMPU to the cost function so that the optimization procedure can continue through variational parameter modification. And with circuits of polynomial depth, the authors are able to report of high fidelity in obtaining the solutions to these two partial differential equations. And to determine whether the algorithm can also be applied in other cases for other partial differential equations, we'll have to make use of the Zalka-Grover-Rudolph or ZGR QFT ansatz. The main objective in introducing this quantity is so that we can position the quantum simulation in an advantageous initial condition so that we can maximize our coverage of the Hilbert space. And this is also related to estimating probability distributions. There are many papers in the literature that have talked about this topic, but this paper that's given more recently from February of this year draws our attention towards ansatz expressibility, in which the authors talk about different ways that you can represent a ZGR QFT ansatz for representing the probability distribution of the quantum state associated with Fn of theta, in which these two ansatz, they're the same in that they have two products that go over the same symbols. However, there's a different quantum operator that acts on the 0 state that's raised to the tensor of n, in which the first ansatz has an exponential of some imaginary prefactor that acts on a quantum state, whereas the second ansatz has a C0 gate, in addition to the multiplication of two exponential factors instead of one that's given in the first ansatz. And we can initialize and variationally modify our parameters for generating solutions to other PDE initial value problems with the following approach. We'll start with the nonlinearity space that's given in the leftmost column for 9 partial differential equations. And the partial differential equations that I've highlighted are the ones that I'm going to present results on in the presentation. But we've also applied it to all partial differential equations in the list. And I've highlighted the DSW partial differential equation system in orange because it's different from all the other partial differential equations, and that we have to make use of a constraint optimization scheme to obtain solutions for the functions u and v of the system. And we impose the requirements for the ansatz that we want to look at the Hilbert space that's the most beneficial as we initiate the time evolution, in addition to potentially imposing initial conditions on first and higher order derivatives of the solution state. And after we formulate our cost function, we can proceed to the cost function ground state, in which we transform the partial differential equation with adder and adder dagger operators, depending on the order of the spatial derivative that appears in the partial differential equation itself. And we form a resultant superposition state to approximate the solution. And we can perform our quantum circuit automation by making use of the open source circ that's provided by Google Quantum AI for assembling our solution approximations. And in addition to making use of circ, we also have to decide which optimizer we should use, in which we have the following optimizer pool. First, we make use of some optimizers from SciPy, namely Infill and SnobFit, in addition to the Nevergrad optimizer that's an open source provided by Facebook. And our third option is a stochastic optimizer that's provided on GitHub, in which we harness probabilistic computation for approximating the minima of a surface through potentially several generations of computation. And the stochastic optimizers that we specifically use include particle swarm, CPSO, CMA, NA, and VDCMA, in addition to a gradient-based optimizer with sequential least squares. And we would like to form or extract measurements for approximating PDE solutions, in which we would like to make use of roughly the following correspondence. We want to make a connection in a frame of comparison between our quantum readout and the classically computed PDE solution. And this is very much like readout that we can obtain from experimental hardware, in which we don't know the exact state of the resultant superposition, much like how Schrodinger's cat is in a combination of being dead and alive before we open the box and determine whether the cat's been hit with radioactive material. And when we're extracting the measurements, the wave function collapses and we have a corresponding Bloch sphere orientation. And for the Navier-Stokes equation, this is the first partial differential equation that we're interested in applying the variational quantum algorithm to. We can look at this partial differential equation with a pressure gradient, in which we have the fluid flow along one dimension, in which the time derivative of the solution U is dependent on a Laplacian term, in addition to a pressure gradient term, in addition to a rho times g of x term, in which we can enforce the convectivity condition on the term rho that appears on the left-hand side, in addition to on the right-hand side of the Navier-Stokes equations, by stipulating that the time derivative of rho plus the gradient of this vector term vanishes. And we can form a cos function for the Navier-Stokes equations with a pressure gradient, which consists of variational prefactors, a third prefactor dependent upon the time step tau, in addition to a resulting superposition taken under the real sign, in which the remaining terms include a Brockett states in mixed Brockett states and adder dagger operators. And we can form a simplification for the cost function and crossing off pressure dependent terms to obtain a far less complicated superposition for Navier-Stokes, in which the prefactors remain the same, but we have a less complicated superposition with a final expectation term due to a quantum operator for the second derivative that appears in the statement of the partial differential equation. And we can make use of this cost function because Navier-Stokes without a pressure gradient corresponds to Couette flow, which physically arises in several different types of instances of computational fluid dynamics, in which there can be different characteristics to the flow along the surface and the boundary of a rotating fluid, in addition to possibly the formation of vortices further into the bulk of the fluid flow. And the analytically known exact solutions have been known to be exponentially decaying curves. And we can simulate the pressure-free Navier-Stokes cost function with both deterministic and stochastic optimizers, in which it draws focus towards an underlying question in our research as to whether the stochastic or deterministic optimizer performs the best. In this case, both the stochastic and deterministic optimizers, they can fluctuate significantly above and below the solution axis when approaching the ground state, which is not desirable. We can also simulate the pressure-dependent Navier-Stokes cost function to recover phases of sinusoidal motion captured in different analytically known exact solutions. And we can also look at applying the variational quantum algorithm to the Einstein equations, in which we know that the Ricci curvature tensor can be expressed as a superposition of alternating signs of derivative of Christoffel symbols, in addition to two other products of Christoffel symbols. And the cost function is given, again, as with Navier-Stokes and all the other cost functions for partial differential equations, a square of a variational parameter, a Brockett mixed state between the solution and its time evolved state, in addition to Brockett states between the time evolved variational state and the stress energy tensor. And we know in the case of the spherically symmetric spacetime, manifold, that the solutions, analytically known solutions to the Einstein equation, can be given by the Schwarzschild solutions, in which the diagonal terms correspond to non-zero components of the Lorentzian manifold. And we can extract measurements from the Einstein equations, in which the optimizer choice can impact the time of all variational state and the measurement at any other time step of the evolution. And we can approximate all other components of the Schwarzschild solution, which are given by implementing different ZGR QFT ansatz for either obtaining a sinusoidal motion or a reciprocal of a power law. And we can form other simulation cases for the stress energy tensor, in addition, including the equilibrium fluid, in which, from our generalized cost function for the Einstein field equations, the form of the stress energy tensor dictates whether any new solution states must be instantiated within the quantum circuit for time evolution. And we can simulate this behavior by knowing the level sets of the solution surfaces for the equilibrium fluid stress energy tensor from a 2021 reference. And we can extract measurements from the fluid stress energy tensor, in which, for the particle swarm optimizer, varying the time step can decrease the magnitude of the quantum readout that we obtain. And we can also simulate the electromagnetic stress energy tensor, in which, from a 1970 reference, we are provided with a decomposition of the stress energy tensor into electromagnetic field and scalar field components. And our strategy for the electromagnetic stress energy tensor is that we can begin with the covariant representation, and we can pass to the contravariant representation by lowering the index and flipping the signs of the electric field in the outermost row and column, while the magnitude, or while the sign of the magnetic field in the 3x3 minor remains the same, which gives hyperbolic secant and hyperbolic tangent solutions. And we also apply the variational quantum algorithm to the Kamasa-Holm equation, in which we encounter computational difficulties for multiplication of variational parameters with mixed quantum states. And we can form various modes of comparison between a 2005 reference, in addition to a more recent 2020 reference, in which we can extract measurements from the Kamasa-Holm equation. And for the Hunter-Saxton equation, we encounter other computational disadvantages, but we're able to at least approximate some parts of the solution, but the solution approximation significantly fluctuates within the first 100 time steps. And we can approximate other PDEs that are given in our paper. And as an outcome or conclusion, we characterize the nonlinear space of 9 partial differential equations. We ask which PDEs can yield a speed up, and we're looking at applying our work in the future. And we would also, I would also like to thank Peter McMahon and my colleague Abhi Sarma, and please feel free to email me with any additional questions.